Let me give you a small analogy here. Can you see the source of light, the torch? Well, it falls on a surface, illuminates it, right? There is a significant intensity of light which starts from the source of light and incidents on the surface in question. But if in the path of that beam of light I insert a medium, let's say that medium could be glass slab, something transparent, made up of any material. What happens to the light which is reaching the surface now? Well, it's safe to say it would be lesser. I don't care about the word less right now. I care more about the word different. By insertion of a medium in the path of light, do you agree that the light incidenting on the surface in question is different? Well, see, medium dependency. That means this constant is actually aware of the fact in what medium are these two charges interacting, quite contrary to the two masses and the gravitational interaction between them. Curious? All right. Let us delve into this further. F equals K Q1 Q2 by R square. K value is 9 times 10 to the power 9 Newton meter square per Coulomb square. But this value is only in vacuum or free space, as they say. What happens if there is a medium in between? This value will change? Absolutely yes, this value will change. Does that mean the force between the two charges will change? Well, let me not commit too early. Let's go step by step. Perfect. This K, constant K, can be broken down into 1 upon 4 pi epsilon. 1 is a constant, 4 is a constant, pi is a constant. So obviously, focus from K is now zooming into something called epsilon. What is this epsilon? This epsilon is actually called the permittivity of the medium. Alright? And this permittivity of the medium is actually a product of two further numbers, epsilon naught and epsilon r. I'll repeat, K is 1 upon 4 pi epsilon. This epsilon is further a product of two numbers, epsilon naught and epsilon r. Epsilon naught is the permittivity of vacuum or free space, and epsilon r is relative permittivity or dielectric constant. If you want an analogy, it's kind of like specific gravity of a substance. Isn't it always measured with respect to water? Specific gravity or relative density. I am not saying exactly same, I'm saying similar. Right? That's what analogy means. The way you understood RD, relative density, or SG, specific gravity, try to think on that line when you think about epsilon r. Okay? So epsilon is epsilon naught, epsilon r. Clearly, what is the value of epsilon r for vacuum? 1. Perfect? Okay. So, K in vacuum, which is 9 times 10 to the power 9, is simply 1 upon 4 pi epsilon naught, because epsilon r value becomes 1. And this epsilon naught, by a simple calculation, can be proved to be having a value of 8.85 times 10 to the power minus 12 Coulomb square per Newton meter square. Okay? As promised, let's come back to what happens if there is a medium. Guys, listen very carefully, because I'm about to bust a myth. I'm about to disseminate a very loose statement which actually a lot of texts make. The statement is, force between two charges when kept in a separate medium other than vacuum changes. I'll repeat. Force between two charges kept in a medium other than vacuum changes as compared to what the force was in vacuum. Wrong. This statement is wrong, because the force between two charges does not change, but the force experienced by each charge alone in totality changes. Confused? Well, even if you're confused, it's okay, because now comes the explanation. Understand something. When two charges are actually in a medium, there is a third party apart from the two charges, which is the medium. What happens is, that, as shown in your diagram, that if F1 is the force applied by Q1 on Q2 and vice versa, there is an extra component force F, which is applied by the medium on the charge. Hence, net force on a charge is not just F1. It is the vector sum of F1 and F. Because they are oppositely directed, the addition of two vectors is actually subtraction in terms of their magnitude. That's why the net force on each charge ends up less than the original force in vacuum. I'll repeat. When two charges are in vacuum, let's say the force is F between them. When you put them in a medium, the force between them is still F, but the net force on each charge is different because the medium participates in applying forces on the two charges individually. Hence, as shown in the diagram, the net force on each charge involved is a vector sum of two forces, one due to the other charge and one due to the medium. The force due to the medium will be oppositely directed to as compared the force by the other charge. Hence, the magnitude of the net force is less than the force in vacuum, and that's where that loose statement comes from, that the force decreases. I hope you got that. Perfect. Little bit on this dielectric constant or relative permittivity of a medium. What does it mean? Well, the physical significance of a dielectric constant is actually its ability to ionize whatever is put inside, to dissociate whatever is put inside. For example, hydrochloric acid HCl, when you dissolve it in water, gets ionized pretty easily into H plus and Cl minus ions. Why? Because the dielectric constant of water is approximately 81, and the electrostatic force between the ions is reduced by a factor of 81, and hence the dissociation comes very easy. That's why usually, as a rule of thumb, the solvents with high dielectric constants are actually good solvents.